Hello, I'm here to talk about one of the most useful tools for analysing and manipulating circuits, the Thevenin equivalent circuit. The use of Thevenin is based around the idea that you can remove an aspect of a circuit and then reanalyze the remaining system so that when replacing the removed component, you can vary the values of this component without the need for recalculations of the circuit as a whole. To simplify this, as shown in the slide, where the top image is a circuit that is to be assessed, and the final Thevenin circuit, which is below, has been simplified to one circuit which contains only one source, one resistor, and a network 2, which in this case simply represents the variable resistor that has been left unshaded in section 1. So in summary, a few reasons when the Thevenin equivalence is useful is when you're required to analyse networks with sources that are not in series or parallel, to reduce the number of components required to establish the same characteristics at the output terminals, or when investigating the effect of changing a particular component on the behaviour of a network without having to actually analyse the entire network after each individual change. The first step in finding the Thevenin equivalent circuit is to remove the portion of the network where the Thevenin equivalent will be found. This is generally depicted as the component or components between the points A and B. In this example, the area left unshaded, that is the 3 ohm resistor, R4, is to be removed and left open for future analysis. So the next step in finding the Thevenin equivalent circuit is to replace aspects of the existing circuit. In this case, all voltage sources presented are to be changed into short circuits, and all current sources are to be replaced with open circuits. After this, the Thevenin resistance can be found. This is the same as normal, where you would use rules such as Ohm's law to determine the resistance, but in this case, it is to be done from the perspective of the removed component between A and B, which is different from doing it in relation to the voltage source. Care must be taken in this step, however, as in some cases, the voltage source being set to a short circuit will make a resistor in parallel redundant and will therefore bypass it, changing the total Thevenin resistance. From this, we can now calculate the Thevenin voltage, which is done by first returning all current and voltage sources to their original position, while still leaving the component between A and B out. The voltage across the points A and B can then be found through either voltage divider rule or Ohm's law. The voltage found from this is to then be used as the Thevenin voltage, or ETH. In the figure given, the voltage across points A and B will be the same as the voltage across the 6 ohm resistor and can be found from using the voltage divider rule. Finally, we can reconstruct our circuit using the values that we have obtained for the Thevenin voltage being our source and our Thevenin resistance being our single resistor in series. We can now replace the removed components between A and B and have a final Thevenin circuit. In summary, step 1, remove the portion of the network where the equivalent is to be found. Step 2, replace the voltage sources and current sources with short and open circuits respectively. Step 3, calculate the Thevenin resistance through the circuit. Step 4, calculate ETH by replacing all sources and finding the voltage across A and B terminals. And finally, step 5, redraw the circuit using ETH, RTH, and the removed component for ease of analysis. Thanks for listening, and here's a list of resources used for the presentation.